going to be talking today about probing 2D materials and heterostructures using atomic force microscopy. We've been actually involved in this since the beginning. You probably recognize Andrei Geim and Konstantin Novoselov, Nobel Prize winners in physics from 2010 for their work on graphene. And in 2005, they actually published a nice paper. I mentioned that at that point, AFM was the only method that allows definitive identification of single layer crystals. So they're initially doing an optical survey and then using their AFM to confirm the existence of the graphene or other single layer crystals, which also in this paper they mentioned that there is a whole selection of different materials that have this layered property and can be used to make single layer crystals. The graphene is pretty interesting, but pretty quickly after that, we start to see these moire patterns where people would take, they would create a multi-layer of a couple or two or more 2D crystals. In this case, we're looking at a monolayer of graphene on hexagonal boron nitride. And first it was observed, this moire pattern that arises because of the lattice mismatch in the materials was first observed in using STM, but then pretty quickly it was also observed in tapping mode topography, which is what we're looking at here in this paper by Yang that came from 2013. In this case, it was about a 15 nanometer superlattice or moire pattern because the twist was around 0 in the different materials. Then we got this a couple of years later, we got a couple of nice papers from Woods and looking at these moire or superlattices using peak force QNM. Peak force QNM allows you to do modulus mapping. So you're looking at the modulus of the material perpendicular to the surface. I mean, it's measuring the bulk modulus, but in a layered material like this, the direction of the measurement is perpendicular. And what we have is two different images that are mapping out the modulus of the material, one before annealing on the left, and then the second on the right after annealing. And what happens is the graphene actually rotates to match up better with the underlying hexagonal boron nitride. And actually, if you look at a 30 micron flake, some parts of this this flake are really moving by quite large distance, like 150 nanometers. And what happens then is you can look at the section profiles across this, and you can see that these peaks get tighter in the modulus. So that's indicating that the lattice misfit is getting concentrated into edges around these hexagons. And I wanted to note that, so here's one example of a mechanical property being used to detect the lattice. But as we're going to see later in this this webinar, Mihir is going to mention using dynamic friction or to also reveal the superlattice with even better reliability. And also LFM has also been used to see it. So mechanical properties in general are often a good way to observe these lattices. But we also mentioned that STM was the first, and conductive AFM was another way that was quickly used to see the lattices. So you can use electrical methods as well. And here are three recent papers